Welcome back to the Explainer. Today we're looking at increased safety, commonly known as XE, which is equipment literally engineered to never spark. We're going to break down exactly how you design hazardous area equipment so an ignition source physically cannot exist. Let's jump right into it.
Right off the bat, let's contrast this with something you're probably already familiar with, which is XI flame-proof equipment. You know, those enclosures built to contain an explosion if it happens inside? Well, XE does the exact opposite. It relies purely on extreme engineering margins to prevent a spark from ever happening in the first place. So we're talking about a completely different philosophy of protection here.
Section 1, Prevention over Containment. So, how do we actually achieve prevention over containment in the real world? Well, there is no thick, flame-proof casing here, no pressurized air, just terminals spaced generously apart, high-quality insulation rated with real margin, and connections torqued so they can never work loose. Add a minimum IP54 rating to keep conductive dust and moisture out, and you've got increased safety. It's protection through good engineering. Full stop. Section 2, Creepage and Clearance Spaces. The foundation of this engineering margin is all about meticulously controlled spacing. Think of XE like giving people plenty of personal space in a crowded room. If nobody's elbows are touching, nobody's bumping shoulders, well, conflict simply can't start because there's no contact opportunity. Terminals work the exact same way. By ensuring enough creepage, which is the surface distance across the insulation, and clearance, the shortest distance through the air, arcing just has no physical opportunity to occur. This gives us a really high level of safety against excessive temperatures, arcs, or sparks, whether under normal operation or even under a specified overload.
Now, these aren't just arbitrary rules. The standards strictly calculate these minimum distances based on the working voltage. For example, if you look at the 690-volt range, it requires at least a 20-millimeter clearance and 25-millimeter creepage. That mathematical rule absolutely removes the chance of a spark jumping the gap.
And as the voltage scales up into high-voltage applications, these mandated distances have to increase dramatically to maintain that exact same preventative safety margin. We're talking clearance distances jumping to 55, 90, or even over 120 millimeters. The crucial takeaway here is that you just can't cram high-voltage EV components into a tiny, cramped enclosure. The physics of the clearance requirement simply won't let you do it. Section 3, the critical T time. So spacing protects stationary terminals perfectly well, but how do we protect a dynamic, heat-generating piece of equipment like an induction motor? Well, for XE induction motors specifically, there's a critical number stamped right on the nameplate called the TE time. This is the exact time it takes the motor to overheat under locked rotor conditions. This sets up a literal race against the clock. At 0 seconds, the rotor locks and stalls, and rapid heating begins immediately. Your protection system has to monitor the current, track the delay curve, and absolutely trip to disconnect the motor before that T time elapses. If you miss that window, a stalled ATEX motor becomes a dangerously hot surface ignition source in its own right. Now, this is exactly where commissioning teams get caught out in the field. A standard thermal overload relay set with the wrong curve or the wrong pickup current can trip way too slowly for the motor's actual TE rating. You absolutely have to verify the protection relay's trip curve against the specific motor's TE time right there on its nameplate. You just can't assume a generic overload setting is going to be good enough. Section 4. No sparking parts allowed. With thermal limits and spacing carefully managed, we arrive at one final, absolute rule. Let's do a quick knowledge check to make sure we're on the same page here. Say an XE junction box design includes a small internal relay with mechanical contacts that spark during normal switching operations. Is this compliant? The answer is, bluntly, no. XE explicitly forbids internal sparking parts ever by design. If a component can spark by design, it just can't be protected this way. It needs an entirely different protection method, like encapsulation, or it has to sit outside the XE enclosure altogether. It's a strict zero-tolerance policy. Also, as a quick best practice to make sure connections never work loose, standards typically dictate you're only allowed one conductor per XE terminal. So you now understand XE's core philosophy. It's all about engineering margin instead of containment. Plus, you know the critical T-trip time rule for motors and why sparking components simply aren't allowed in this method at all. But this leaves us with a really provocative question for next time. What if we didn't just space things out? What if we starved the circuit of energy so completely that even a dead short couldn't ignite anything? In our next explainer, we'll cover the opposite extreme, the smallest energy protection method of them all, intrinsic safety, and the barrier devices that make it work. Catch you then.